So, welcome again to this new lecture on of the course Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we were doing earlier. So, in the previous few lectures we looked at the defect equilibrium. So, basically we estimated the concentration of defects for stoichiometric cases in which there is only temperature dependence is there for all the concentrations, and then we looked at the non-stoichiometric cases where you have temperature as well as partial pressure of oxygen dependence. So, we looked at the case for oxygen deficient oxides in which you can have vacancy of oxygen as well as metal interstitial, and we looked at the case of MO2. So, MO2 will have VO as well as MI as dominant defects. So, we looked at the cases when vacancy of oxygen dominates, we looked at the case when metal interstitial dominates, and we looked at the case when both of them coexist. So, as a result you have a mixed kind of plot that you get. So, if you recall, when we plotted this log of concentration versus PO2, you had a dependence which was something like this, and other defect went like this. Okay. So, in one case, all right, so it is a little bit steep actually, so it could be a little bit something like that. Okay. And then electron concentration will go on top like this. So, in one case you have vacancies dominating, in the other case you have metal interstitials dominating as a function of partial pressure of oxygen, and they will all have different dependence on partial pressure of oxygen. So, now let us look at the cases of metal deficient oxides. So, and let us look at the example of so oxide type is MO. So, MO can have either vacancy of metal or oxygen interstitial. These are two possible defects that you can have. So, assuming that, so in this case we will just proceed with the metal vacancies. So, if metal vacancies dominate, then you can do for a MO kind of oxide, the oxygen in the system enters from outside. So, oxygen goes to oxygen site. For maintaining the site stoichiometry, you will form a metal vacancy, so that you have MM/OO ratio is 1. So, you create this site which is vacant, and as a result you give rise to two holes to maintain the charge neutrality. So, equilibrium constant for this reaction can be written as OO into Vm into NH square divided by PO2 to the power half. So, if we say that OO is equal to 1 and Vm is very small as compared to OO, then one can write K being equal to Vm multiplied by NH square multiplied by PO to the power minus half. Okay. So, and what is the electrical neutrality condition? The electrical neutrality condition says that NH is equal to twice of Vm. You create two holes for every oxygen metal vacancy, and as a result you can now substitute this to calculate what is Vm, which is equal to half of NH. This will become equal to K divided by 4 to the power 1 by 3 into PO to the power 1 over 6. So, in this case you can see that concentration is proportional to partial pressure of oxygen, but it is the other way around. So if you plot log of concentration as a function of PO2, now the defect concentration increases. So basically this is 1/6. So this is for Vm, and you can plot a similar line for, this would be NH. Okay. So you can do the similar exercise for oxygen interstitial as well, which we will not do. The third case could be the case when intrinsic ionization is strong. So we looked at the case of oxygen deficiency, we looked at the case of metal deficiency, and then we look at the case of third case is intrinsic ionization. And this is something that can happen in any system. So what it would mean is basically formation of electrons and holes. This is equal to E plus H, and again this is stoichiometric, it does not change the stoichiometric. So in this case, let us say Ki is the reaction constant, then this will become Ne into NH, and Ne being equal to NH, you can write Ki to be equal to Ne square or equal to NH square. This is for intrinsic ionization in case when. So again this is similar to stoichiometric defects. Okay. So in this only dependence on because K is always equal to exponential of minus delta G divided by RT, and delta G is nothing but delta H minus T delta S, and this basically is nothing but enthalpy of formation of defects. In this case it is intrinsic ionization. What is the intrinsic ionization enthalpy? It is nothing but band gap, right. So if you have a system like this where you have a EC, EV, so to create the electron hole pair you need to excite an electron, make it go here, and you form a hole here, and the energy that you need to overcome is the band gap. So in this case its defect formation energy in this case is nothing but the band gap of material. Okay. So this will be nothing but similar to band gap of the material, and again it is independent of temperature, it's independent of partial pressure of oxygen, it's only dependent upon the. So let us see, now let us make a broader picture. So suppose you have a oxide, dielectric oxide. So basically what happens, at a broad range of ambient conditions. So how can you define them? The first condition can be low partial pressure of oxygen, which means heavily reducing conditions, right. So heavily reducing conditions. Then you can have intermediate PO2, which means it is moderate, or we can say ambient sort of conditions, right. It can depend upon oxide to oxide, but let us say it is ambient for the case that we have, and then we have high PO2, which is heavily oxidizing. Now from the previous analysis you can see low partial pressure of oxygen leads to what kind of defects? Basically when you reduce the oxygen concentration in a material, you create more and more vacancies of oxygen. So under this condition VO, let us say, is the dominant defect. Let us not consider metal interstitial, let us just consider VO. What will happen at high PO2? You will have metal vacancies at high partial pressure of oxygen, and then we have intermediate range, we have oxide is stoichiometric. the stoichiometry does not change. So, you form stoichiometric defects. Those stoichiometric defects could be Schottky defects or Frenkel defects, or it could be electron hole pairs, but there is no change in the defect chemistry at intermediate pressures of oxygen. So, let us say, in this case, let us consider instead of Vm, let us consider OI. Okay. So, we consider OI and VO. So, the dominant defects are oxygen vacancies and metal interstitial. And when you have this kind of oxygen interstitial plus vacancy of oxygen, for them to go in tandem across various ranges of oxygen pressures, the combination of OI and VO gives rise to what kind of defect? We have anti-Frenkel defects. Okay. If it was Vm, it would have been, if it was VO and Vm, what would it have been? Okay. So, accordingly you will have the defects formation at stoichiometric condition. So, if you consider VO and OI, then the defect that will form, that is likely to form under stoichiometric condition, is anti-Frenkel, and if your combination of defects is VO and Vm, then you are likely to form Schottky defects. So, let us say we first consider low partial pressure of oxygen situation. So, let us say we first consider low PO2. If we consider low PO2, then the defect reaction can be oxygen at oxygen site goes out. Okay. It gives rise to formation of oxygen vacancy, and then this is compensated by a formation of 2 electrons. So, we consider only electronic compensation, let us not worry about ionic compensation, otherwise you can do in terms of ionic compensation. And let us assume that activities of metal on metal site and oxygen on oxygen site is equal to 1. Okay. Then we can write this reaction as, the reaction constant for this is let us say, so this is a reducing reaction, we can write this as Kr. Kr will be equal to PO to the power half into VO into Ne square. Okay. And Ne being equal to twice of VO, we can write this as Ne divided by 2. This is equal to VO. This will be equal to Kr divided by 4 to the power 1 by 3 into P to the power minus 1 over 6. This will be my first expression for carrier concentration for the low PO2 condition. Now, let us look at what will happen at high PO2 condition. At high PO2, we know that we have more oxygen in the ambient. As a result, oxygen gets into the system. So, let us say oxygen goes to interstitial site and then it forms 2 holes, all right. There is no site conservation problem because oxygen goes to interstitial site, does not go to lattice site. As a result, we do not need to create or destroy a site. So, now this is oxidizing reaction, then for this accordingly you can write divided by PO to the power half, NH being equal to 2 of OI, you can write half of NH being equal to this is going to be equal to, you can write this KO divided by 4 to the power 1 by 3. Okay. Okay, and then it will be PO to the power 1 over 6. Okay. So, this is my second concentration of carriers. Now, what will happen at stoichiometric conditions? Now, third is that is moderate PO2, okay, partial pressure of oxygen. So, under these two scenarios might happen. The first scenario is intrinsic ionization of electrons and holes. So, if the band gap of material is small, then there is a possibility you might form intrinsic ionized defects. So, in such a scenario, your defects that will form is E plus H, and in this case Ki would be equal to Ne into NH, all right, which is equal to Ne square, which is equal to NH square, because Ne is equal to NH because of electrical neutrality. Second scenario that might occur is, so this is third one, and the second scenario that might happen is formation of anti-Frenkel defects, okay. So, which means oxygen at oxygen site goes to interstitial, and as a result it forms a vacant sites of oxygen. So, I can write this K anti-Frenkel as OI into VO, and this is equal to OI square or VO square, because VO is equal to OI because of electrical neutrality. So, this is another reaction. I can write this as KAF. So, okay, and if you consider these four reactions, then you can, so I will leave that for you to prove, but you can write KF into KI square, sorry, KAF into KI square is equal to KR into KO. This is a relation that you can write between the all four reaction constants. So, if you now do the similar analysis, okay, so you have a regime of high PO2. So, when you plot this as a function of, let us say, so this is log of certain kind of defect, okay, N means defect, and as a function of partial pressure of oxygen. So, you might have multiple scenarios, right. So, you can distinctly draw three regions. So, this is a region of, let us say, intermediate PO2, this is high PO2, and this is low PO2, okay. So, let us say if OI and OVO were, let us say if the anti-Frenkel defect dominated, if anti-Frenkel defect dominated, then in this region your VO will be equal to OI, and there will be certain concentration, okay. The thing is, these defect concentrations must remain continuous as they go across partial pressures of oxygen. So, at lower pressures of oxygen, we saw that the dependence is -6, sorry. So, if you just keep continuing it in the lower region, it will be -6 dependence of VO, and if you do the same analysis as we did in the last class, you can form. So, in the high PO2 region we have found oxygen interstitials, but then again combining all four equations you can find the expression for VO as well. The VO will go something like that in this region, and the OI on the other hand, now VO is equal to OI, the OI follows this pattern in this. So, this is for OI and it will follow something like this in this region, okay. And the electrons and holes, so in this case the electron will be like this, and the electron will be, they will follow something else in the other region, and the holes will follow this kind of thing. you need to follow what their behavior will be in the intermediate regions. So, let us see how do we do that. We want to make a plot of these defects, which is called as Brewer's diagram, which allows us to determine the defect concentrations at various pressures in a given dielectric or oxide ceramic. Okay. So, for that we need to consider the limiting conditions. Okay. So, limiting conditions first. So, we need to determine what are the limiting conditions. So, basically how will these transitions occur, where will you put the boundaries, and how will the electron and hole concentration will take place, let us say if the anti-Frenkel defects dominate. So, let us say first condition is low PO2, which means oxygen deficit. Okay. So, if this is the case, then we can assume that VO is basically equal to half Ne, which is greater than OI. Okay. So, we can write VO being, so we have just written that VO is equal to half Ne, this is equal to Kr divided by 4 to the power 1 over 3 into P to the power minus 1 over 6. This is how we determined. Now, OI is nothing but Kf divided by VO, all right. So, this becomes Kf divided by Kr to the power divided by 4 to the power 1 over 3 into P to the power minus 1 over 6. So, which means this becomes Kf into Kr divided by 4 to the power minus 1 over 3 into PO to the power. So, you can see that this is plus 1 over 6, and you can also, so we have determined VO, we have determined Ne, we have determined OI, and we now need to determine what is NH. NH is equal to Ki divided by Ne, and this is going to be equal to, basically you can write the expression Ki into 2 of K R to the power minus 1 over 3 into PO to the power 1 over 6. So, we have determined the 4 expressions, the first for VO and Ne, second for OI, and this for NH. And what is the limiting condition? Limiting condition is VO is a lot greater than OI. VO is a lot greater than OI. So, if you now, we know the expression for VO, we know the expression for OI, from this you can get what should be the PO2. The PO2 will work out if you combine these equations, the limiting condition will be so you just write basically Kr divided by 4 to the power 1 over 3 into PO to the power minus 1 over 6, this is greater than Kf into Kr divided by 4 to the power minus 1 over 3 into PO to the power 1 over 6, and just manipulate the terms, and what we will get is basically, so you have only three terms here, one is Kr, second is Kf, and third is PO2. So, we will get PO2 must be less than Kr square divided by 16 Kf cube. This is the relation that you will get. So, this is the limiting oxygen partial pressure, that PO2 must be smaller than Kr square divided by 16 Kf cube. And what is Kr and Kf? Kr is nothing but minus delta exponential of minus delta Hf by Kt, and Kf is nothing but exponential of minus delta H of anti-Frenkel defects divided by Kt. Sorry, this is Af, not anti-Frenkel, but that is okay. I mean, so we can write Kaf similar to Kf. Yes. Okay. Frenkel, anti-Frenkel, it just can be interchanged. Okay. So, this is the limiting pressure for low PO2 conditions. Now, let us see what is the limiting condition for high pressure condition. So, for the high pressure condition, the situation was OI was equal to half of NH, which should be greater than VO. So, now the limiting condition for high PO2. So, for high PO2 we can write OI, this was equal to half of NH, and this must have been greater than VO. Okay. OI, expression for OI we know, which is equal to half NH. This is equal to KO divided by 4 to the power 1 by 3 into PO to the power 1 over 6. So, we know that VO is equal to KF divided by OI. Okay. So, if you do that, we can form an expression for VO, which is equal to VO will be equal to KF into KO divided by 4 to the power minus 1 over 3 into PO to the power minus 1 over 6. Okay, that is how it will vary. Similarly, we know the NH, NE is equal to KI divided by NH, and this can be worked out as KI into 2 KO to the power minus 1 over 3 into PO to the power minus 1 over 6. So, one thing you can see that no matter what the situation is, VO and NE always go as P to the power minus something, and VO, OI and NH always go as P to the power plus something. So, basically what it says is that as you increase the partial pressure of oxygen, and that makes sense, as you increase the partial pressure of oxygen, the oxygen vacancies come down, the electron come down in number, but holes and oxygen interstitials will increase in number. So, again using this equality which is written on top, using the condition on top and concentrations of OI and VO, we can determine that PO2 will be, in this case, PO2 will be greater than 16 Kf cube divided by KO square. So, partial pressure of oxygen must be greater than this number. In between the two, we will have the stoichiometric region. So, we will stop here, we have run out of time today. So, in the next lecture, we will finish this stoichiometric part and build the whole diagram to see how the variation of defects concentration as a function of PO2 looks like. Okay.